Welcome to our Data Bytes workshop. This is Better Data Management. And there is a link at the bottom there that will take you straight to the slides if you would like to download them. I am Bjornen. I am the Research Data Initiatives Librarian here at OSU, and my colleagues, including Clark, who's on the workshop with us, do a workshop on a weekly basis throughout the semester and just try and offer you some knowledge that you won't get probably through your class work or through other normal channels. But we like to think it can sure make your life a lot easier if we can teach you some new and important things. So let's start out by talking about what we're going to cover here. And I first want to talk a little bit about why I teach these workshops on data management and why I think they're important. And then we're going to cover a series of 6 different better practices, things you can do to make sure that your records are organized and that you have data that you can use in a meaningful way. And then at the end, I've got some contact information and some links to some resources that hopefully will help you. So the question about why data management, the answer is that increasingly in recent years, research has changed. Research is no longer just about a publication or doing the work just to get a publication or a thesis if you're a student. It is about creating the data that is actually the main product of your research. And increasingly, we recognize that publications are really just a snapshot, and usually an imperfect one at that. But if you have done a good job of creating data and documenting data, and we'll talk about all that, then that product can not only be used by others in your direct research area, but it can actually be used in groups that are well outside of your research area. And so we're going to try and convince you why that's important. Just for your own purposes, increasing or improving your data management improves your own chance of research success. If you can find your data, if you can read your data, if you can remember what you did and not realize that you left gaps in your data, then that's going to increase the odds of being successful and not having to repeat things. So that's some of the reasons. It's easier to analyze and communicate when you're at the end of your project and you're trying to write it up. Those are the things that are going to be important, is you need to be able to provide that data in a form that other people can understand and use. And for the purpose of long-term project sustainability, if your project is successful, you're not going to be the last person that cares about it. You're going to want to be able to hand off that project. A lot of times graduate students, if you initiate a successful project, there's going to be others that are going to come on behind you and do the next phase of it. And so leaving good records, leaving good data is going to make it much, much easier for the person who comes behind you. So with that, I am going to share a little quick video. And this video is, it was originally developed by NYU Health Sciences Center librarians, and it's become a bit of a classic. So let's see if I can start it for you.
Hello. My name is Dr. Judy Bjornen. I'm an oncologist at NYU School of Medicine.
Hello, Dr. Judy Bjornen.
I read your article on B-cell function. I think that I could use the data for my work on pancreatic cancer.
I am not an oncologist.
I know, but I think I could use the data for my work on pancreatic cancer. Do you have the data?
Everything you need to know is in the article.
No. What I need is the data. Will you share your data?
I am not sure that will be possible.
But your work is in PubMed Central and was funded by NIH.
That is true.
And it was published in Science, which requires that you share your data.
I did publish in Science.
Then I am requesting your data. Can I have a copy of your data?
I am not sure where my data is.
But surely you saved your data.
I did. I saved it on a USB drive.
Where is the USB drive?
It is in a box. It is in a box at home. I just moved.
But can I use your data?
There are many boxes. So many boxes. I forgot to label the boxes.
Hello again. Thank you for sending me a copy of your data on a USB drive. I received the envelope yesterday.
You are welcome, but I will need that back when you are finished. That is my only copy.
I did have a question.
What is your question? You might find the answer in my article.
No. I received the data, but when I opened it up, it was in hexadecimal.
Yes, that is right.
I cannot read hexadecimal.
You asked for my data and I gave it to you. I have done what you asked.
But is there a way to read the hexadecimal?
You will need the program that created the hexadecimal file.
Yes, I will. What is the name of the program?
Cytosynth.
I do not know this program.
It was a very good program. The company that made the program went bankrupt in 2007.
Do you have a copy of the program?
I do not use this program anymore because the company that made it went bankrupt. Maybe you can buy a copy on eBay.
I have good news.
You again.
I talked to my colleague. She knew a person with a copy of the software.
Then why do you need me? Everything you need to know about the data is in the article.
I opened the data and I could not understand it.
If you have the program, you will find it is clear.
Well, I noticed that you called your data fields SAM. Is that an abbreviation?
Yes, it is an abbreviation of my co-author's name. His name is Samuel Lee. We call him Sam.
I see. And what is the content of the field called SAM1?
Ah yes, SAM1 is the level of CXCR4 expression.
And what is the content of the field called SAM2?
That is logical if you think about it.
What is the content of the field called SAM2?
I don't remember.
What about SAM3? Is there a guide to the data anywhere?
Yes, of course. It is the article that is published in Science.
The article does not tell me what the field names mean. Is there any record of what these field names mean?
Yes. My co-author knows what the content of SAM2 is, and SAM3. And SAM4.
Can I talk to your co-author?
I'm not sure.
I would very much like to talk to your co-author.
Well, he was a graduate student. He went back to China 2 years ago.
Can I have his contact information?
He is in China. His name is Sam Lee.
I think I cannot use your data.
You could check the article to see if what you need is there.
Please stop talking now.
Okay. So hopefully that convinced you of the advantages of creating good records for your data. And of course, I'm here to convince you about the benefits of data management, but perhaps the opinion of funding agencies you might consider to be more important. And there has been a significant effort by the most of the federal funding agencies to encourage data sharing, and as a result, data management. This is taken from USGS, from their science manual, their staff manual. And I wanted to highlight a couple of things because they make it very clear that they consider that their research staff, when they collect data, they are not collecting data for a one-time use, that data has value, and that they expect that all USGS scientists will save their data in a form that makes it discoverable, well-described, and preserved for access for use beyond the life of research projects. So with that, let's talk a little bit about the different kinds of data and about what kind of challenges that you may have with regard to preserving and managing that data. So I have it broken down very generally into 4 different categories: lab data, field studies, human studies, and computational. And it is entirely possible that your research project may overlap, 1, 2, 3, or all 4 of these. So as we talk through this, be thinking about, which of these actually apply to you and what you do. So when you are dealing with lab data, some of the challenges that laboratory data may generate is that you may have data being collected from a variety of different instruments or processes. And in a lab, it's very likely that there are multiple people using the same instruments. So you may have to segregate your data from that of others that are in your work group or others that use those instruments. There may be a mix of file types. You may generate raw data from an instrument, but the output that you actually care about or save is actually an analyzed file. And it is oftentimes, if it's a commercial instrument, those files are a proprietary file type. So you may not be able to actually preserve the raw data in a meaningful form. You may have the data stored in a number of different places. You may have a lab computer. There is data stored on the hard drive of the instrument. You may have it on your own personal device where you are doing some of the analysis. So keeping those different places where you have data organized is another challenge. And I've already covered this last bullet point. Field data is another type of challenge. Field data is very often, I'd say usually, recorded as a hard copy. I've had people who do field studies tell me over and over again how challenging and difficult it is to collect data on an electronic device in the field. And so if it's recorded as a hard copy, then preserving it is a problem, transcribing it is a problem. The very few of us these days use data in handwritten form, so it usually has to then be transcribed into a digital form. And it may be collected, in field studies, it's very often, they may go on for years, and then maybe a number of different graduate students or technicians that collect that data, and each one of them may have their own way of doing it. And very often with field data, you may have very large data sets collected from sensors or from geospatial data that goes with the field data. So all of these things can make it a problem to collect consistent records and keep them organized. Human studies, the biggest concern is usually privacy and keeping your records in such a manner that personally identifiable information is separate or coded. Maintain, again, it's often unstructured, so making sure that it's collected in a consistent fashion. and that it has adequate descriptive or metadata stored with it so that it's meaningful later. And it too, human studies also can last for a very long time. And computational data sometimes and increasingly is a very large data set, and it too can be unstructured. It may be stored in a cloud environment. It may need to be stored in multiple places for backup. And again, documentation and metadata is important. And if you are doing a large project with computational data, you may be collaborating with people at other institutions or even in other countries. And things like access and file transfer for data sets like that can be a problem. Common to all research, organizing and analyzing the data. Once you have it, you need to be able to prepare it for publication. You need to be able to meet publisher and funder expectations or requirements. So if they have an expectation or a requirement that your data will be shared, you have to be planning for that. And that is much easier at the beginning of a project than it is at the end of a project. And archiving the data at the end of the project, again, is something that planning for it in advance, you have more options, and it's a lot easier to create that infrastructure that's needed for that. Finally, we will not get into it in this workshop, but we talk about it in other workshops about the problems of research reproducibility or replicability and even repeatability. And the difference between those is reproducibility is the big picture of being able to look at a study and be sure that the outcomes of it meet the research questions, or the research questions can be answered with a different study and receive approximately the same results. Replicability means somebody else coming along and doing your same experiments and getting the same results. And repeatability means you need to be able to repeat that experiment and get the same results. Again, if you have not done an adequate job of documenting exactly your methods and the process, all three of these things will be challenging. All right. Again, let me stop here and ask if there's any of you all that have thought about these things. Is there anything you would like to, you can unmute yourself, or you can drop in the chat if you have anything that I may have overlooked that you'd like to mention. Any challenges with research that you've done to date that perhaps data management could help with? All right, let's go to our better practices then. The first one is better practice 1, plan for the entire data lifecycle before collecting any data. So we've already touched on this a little bit, and that is begin with the end in mind. So when we talk about the data lifecycle, the research lifecycle, if you are not familiar with that and do a Google search, you will find multiple different versions of this. This particular one is taken from ICPSR, and we'll talk a little bit more about ICPSR. It is an organization which has a data repository, mostly for political and social science research. And we'll talk about this too. They are an excellent resource for information about data management and learning, educating yourself about taking care of your data. So if we look at this, you see they have it broken down into a total of 6 different steps, We all know that when you're doing research, it does not progress in a nice linear fashion. So you should take this with a grain of salt, but I'll draw your attention to the first phase, which is where you are creating your proposal or planning your research. And one of the things that they highlight is that is the place where you should be creating your data management plan, commonly referred to as a DMP. And DMPs are required for most funding proposals. And the funding proposals are, when you submit that, it is usually about a 2-page addendum to the proposal where they ask you to describe in sometimes great detail exactly how you're going to take care of that data. Where is it going to be stored? Who's responsible for it? What kind of backups do you plan? What file types and so on? We'll talk about that some more too. Anyway, the DMP is not just important as a 2-page thing you throw together to include with your proposal. It is most helpful if you consider that you are doing it for yourself. It's going to help your research processes go better because you've thought through all the things you need to be doing upfront. So let's see here. If I skipped anything, let me check my notes here. Okay. Data management plan. So this is a little more information about what that would look like. Basically, it starts out by, when you are doing your plan, you should be thinking, I'm probably not starting this project from scratch. Who else has done this kind of research? What kind of, not just publications, because we're all well trained to go look for publications that support, past work. It's also useful to go look and see what sorts of data sets are out there that have already been generated and how can they potentially be incorporated into your research project. Consider what kind of formats you are going to be collecting data in and whether or not there are things like intellectual property that you'll need to protect. And again, very important to consider this upfront because there are processes, certainly at OSU and virtually every university, that where if you expect to generate intellectual property, i.e., is your work going to be patentable, you need to be going through the hoops right up front. Who else may want to use this data? And so if you expect that your proposal will be a part of a bigger picture, you want to think about how, the same way you thought about, well, who else has data out there that's public that I can use? You want to think about how you can make your data public for other people to use. And down at the bottom there, I have a link to a helpful web-based tool. The most useful thing about this, it's called dmptool.org, is that it has templates for different funding agencies. So if you are getting ready to submit a proposal for USDA, for the NIFA program, you can go in and find templates for that particular type of proposal where it will coach you on the different things that should be incorporated in that type of DMP. One thing to note, I think part of the reason why very often, in my experience, DMPs are thrown together at the last minute is because people feel that they don't matter, that reviewers don't actually look at them, and so they don't have to worry about that. The truth is that is not true. It does vary significantly from not just organization to organization, but also reviewer to reviewer. And so it's not a good idea to assume that no one's going to look at your DMP as long as you have that 1 or 2 pages attached, that's all that matters. Because increasingly reviewers do care about that and want to see that you've thought through all these things when you submit a proposal. Okay, so now let's talk about data storage. My experience at OSU is that this is the thing that flummoxes researchers new to campus the most. And it's because we tend to leave decisions about what kind of storage is needed and what kind of resources to departments or colleges. There's no consistent policy, there's no consistent guidelines across the OSU universe. So when you are exploring this, you need to know where to start. You should also distinguish between whether you're talking about data storage during the life of the project, or whether you're talking about the long-term storage, again, for making your data available after your project is complete. And you should consider whether you would like to have access to that data after you leave OSU. Whether you're faculty or a student, you probably are going to be building off of this research that you're doing, and you may very well want to have access to that data. Be aware that there is in progress right this very moment as we speak, a new research data ownership policy at OSU. In a general, in a nutshell, if no one else has claimed ownership, i.e. if it does not fall under the purview of a funding agency or there's some other criteria where that data belongs to someone else, it belongs to OSU, okay? This is something that I think students commonly don't recognize. And so it does not mean that you will not have access to that data, but it does mean that you need to be conscious of that fact, and that when you leave OSU, you will need to be sure to leave the appropriate records behind with the data. So what are some data storage options? Frankly, the only across the board option is that when you receive an OSU email address, you also receive an OSU OneDrive account with that email, which has 1 terabyte of storage, which sounds like a lot, and it is a lot, but there are limitations to that. For one thing, the way OneDrive is structured, it's really only useful for documents, because it's doesn't allow easy upload and download of data and accessing data in pieces, okay? Many departments have server space. So for instance, the College of Arts and Sciences, we know who to have you contact. They will set you up with space on their server. But it's not universal. Not all colleges have that. So other options, you may want to purchase an external hard drive to do backups or to store your data on. There are commercial options like Amazon Web Services, and there are less elegant options like Dropbox, Google Drive, etc. Keep an eye on the size and quantity of data you're going to save, because if that gets too large, it may cost you, and you'll want to plan for that. Okay, so those are options to explore while your project is in progress. And so that's for the short term. The long term, what you need to look into is a data repository, especially for projects where the funder expects you to do data sharing. So after the project is complete and the publication is out, you want to be sure that your data is going to be available to anyone who would like to follow up and is interested in your research. One of the things to be aware of is that increasingly there is an advantage to saving your data or storing your data, archiving your data separately from your publication. One of them is that there has been some studies done recently that indicate that publishers are not good stewards of your data. So some of them will offer you the option of letting them archive your data, but the papers that have been published indicate that it's possible that the links may be broken and that actually that data may not be very accessible at all. So that's one thing to consider. Another thing to consider is simply your own best interests in terms of, by storing your data in a reputable data repository, you make that data available and discoverable. So it can be discoverable through a Google search. It can be a Google Scholar search. It can be discoverable. It depends on the repository. But if it's a disciplinary repository, you're obviously going to get more traffic from people that work in your area. All those things go into deciding what repository to use. And that's a little beyond the scope of what we can talk about today. But I'm happy to talk to you about repositories if you need more information. One option to, another important thing is any repository that you do decide to store your data in should have a persistent identifier, like a DOI. So it's a link that'll stay with that data and won't break, like the publishers. Okay, so one option is to consider using ShareOK. ShareOK is the institutional repository for OSU, and it is, I believe, certainly the most convenient. It does increase the visibility of your data, and so if you go to the web page, the URLs down there, it really just involves creating a form to tell the repository managers that you want to deposit that data. This may not be your best option if your data is a very large set or that you anticipate creating different versions over time and that all of those versions you want to have accessible. So fast and easy, but not necessarily the easiest to use once you have deposited your data. So let's talk about some other possibilities for data repositories. There are two general categories. One is a general repository where you can deposit any kind of data. And so some examples of that might be something like Figshare, Dataverse, etc. There are also disciplinary repositories. And if you work in a discipline where there is a lot of work with open data, it is very likely that you will have access to a disciplinary data repository. If not, consider one of these. So ICPSR is, as my colleague Clark likes to say, the gold standard for social science data. I mentioned that one of the reasons for that is that they provide, and this is just a snapshot of the homepage, they provide all kinds of resources, training, they have tutorials, they have the link down at the bottom there is just a PDF for that with information about how to prepare your data and archive it. So when I was mentioning the importance of planning ahead for your data and looking at data repositories, this is one of the reasons, because depending on the data repository that you select, they will provide you guidance for things like creating the metadata that you need to save with that data. Data One is another resource. It is not strictly a repository. It is a network, a cyber infrastructure that supports 44 member nodes. The member nodes are all repositories, and most of them fall within this category of earth science, ecology, environmental science, and some social science. It is NSF funded and NSF developed. So from that standpoint, it's a solid resource. And they provide governance to all the members' repositories, the nodes, to make sure that the data that is accepted is curated and, again, good discoverability through good metadata. I didn't mention that ICPSR, there are two different options for using it. If you choose to deposit your data there, one of them is what they call self-curation. And so you're the one that creates the metadata and stores that data. They also offer a curation service. And so depending, if your university is a member of the ICPSR consortium, then my understanding is it does not cost anything. But it's important to investigate that up front. And again, going back to, if you are creating a data management plan, you need to know that up front, because one thing you are allowed and even encouraged to do when you write up your grant proposal is to include a budget line item for data curation. So if you need to pay for manpower or a service such as ICPSR to do the data curation, do it up front so that you know you've got that funding covered. All right, so I had an example here I was going to do, but I think I may be running short on time. Let's take a look here. Let's just go to there we go. Okay, so let's just real quickly here take a look at what this looks like. So this is Data One, and you see that up here it talks about the different services that are offered. But if you are looking for a data set that meets some need, whether it's for your research or for a class project or a proposal, this is where you would go to find data. And so let's just very quickly throw these terms in here and let's see what pops up. Okay, first thing I'll draw your attention to is that there is a map interface. So if you know that what you really want is information about data sets about the oil spill in the Gulf Coast, you could go down here and click on this, and that would take you to the data sets that are available in that area. Here it says we have a total of 47 data sets. And so this, you could scroll through and look and see what all of them are. And let's say that this was, what you really need is something very, very current. And so what I want is, I only want something that goes from about, let's see what that is. We want data. Oh, but there's a differentiation. It's between the data coverage and the publication year. So let's say we only want data published between 2010. Okay, we can do that. And then we see that it narrows it, and that data is what we would look at. Okay, so that's what that looks like. So let's go back to the other screen. Let's say that, and the other thing that I should have shown you and I didn't was you can see what repositories are in Data One, and you can search them individually if you want to. If you know which data repository is the one that's appropriate for you, then you can go in and look at that repository and do a search in that repository alone. Probably it's more likely that you don't know what repository to look at. And so using a registry allows you to do a search and look at, where do I find a repository to store this particular type of data? And so re3data.org is one option, and there are others. But anyway, it's a simple thing. Again, you would enter your search terms and say, how do I find a repository? Used to be re3data tended to be a bit thin on US data repositories, but recently it seems like they've expanded that, and so now there seem to be a lot more US repositories represented. All right, better practice 2. One of the things with data collection is that when you are collecting it, you want to minimize opportunities for error. So there's 2 ways to do that. One of them is to minimize the error up front, make it as hard as possible to enter data that is incorrect. And the other way is to find some tricks or develop processes for quality control. It improves the consistency and minimizes errors. So let's just look at a couple of quick examples here of templates. This one came from the USGS. You can see it has a lot of drop-down menus. So you can choose what kind of sample media is being analyzed, the date range, and so on. And because they're predefined, the data goes in there in a consistent format. So things like dates all go in exactly the same format. So that is one advantage to a template. This is a different kind of template. This one could be set up in a Google form. And again, one of the advantages is that by using a form that's in the cloud, it allows you to require that the data as you enter it has to meet certain field requirements, and you can spell that out. So lab and field notebooks. This is where, again, a lot of errors can be introduced because people handwrite in them. It may include unstructured data like observations, and every time that you transcribe from a lab or field notebook, you have the option or opportunity to have errors in transcriptions. One way to get around that is to create a template and put it in the front of your lab or field notebook. If you're a research supervisor, you can require that people in your group use this in their notebooks, and it has to have a consistent fields in consistent order, data entered in a certain way. That is one way. Another way is to if it's your notebook, you can cut and paste, but it still has to be digitized. I include a little link down here where if you're keeping a lab notebook, there are rigorous guidelines around how that should be done. Again, especially if you're concerned about intellectual property. So if you're not aware of that and that is something you have to do, then I encourage you to follow up and look at that. It also varies somewhat between, say, field notebooks for geologists versus lab notebooks for chemists or biologists. All right, better practice 3, determine roles and responsibilities. And why? Because if you don't know who's supposed to be doing it, nobody will do it. I had an experience where I was consulting with a faculty member, and as I was asking her questions about who, or about her backup practices, how often do you do backups? She said, well, my graduate students are supposed to be doing it weekly. But she got a funny look on her face, and it was very clear that as she was telling me that, she was not at all convinced that that was happening. So one thing you can do is, identify those roles up front. This is also something that will need to be included in a data management plan. They like to see who's going to take care of these things. So some of the things that need to be, delegated, and you need to know who's going to be doing it, backups, who's going to review data. Of course, if you're maintaining a notebook for, again, as a legal document, you have to have regular reviews, and somebody needs to go through and check the data. Another thing is that because a data management plan, or DMP, is what we call a living document, which means that no matter what you write up when you start a project, things change invariably. Methods that sounded like a good idea don't pan out. And it's important to update the DMP when you make changes to your processes. The DMP should always reflect things as they actually are happening, not as you thought they should happen. So someone will need to, on a regular basis, go in and update that. That actually is something that, again, should be filed with annual reports for grant documentation. So again, if you do it as on a regular basis, then it prevents having to go back and do it annually. Data security, who's going to monitor that? Who's going to check for corrupted files and be aware if somebody that shouldn't be getting into your data is? That's another role that can be assigned. And who is going to be responsible for a process, a checklist or whatever, so that paperwork, files, data is transferred when someone leaves the lab or leaves the research group, or when they come in, who's going to sit down with the new person and go through the new procedures. Instrument calibration and documentation. And the last one I encourage is consider who's going to be responsible for going through periodically and determining that things are obsolete and need to be deleted, because I guarantee scientists are hoarders. And if you don't have someone designated to do that, eventually it just piles up. It makes it hard to find the important stuff, and it eats up your storage space. Okay, there we go. Okay. If you've taken any of our other workshops, you may have already come across this, but we encourage developing a standard file naming protocol. Ideally, again, this is something that is implemented at the top of the research group, and everybody utilizes it. But even if that's not the case, if you're a new graduate student, by all means, go in and create your own standard file naming protocol and stick with it. So just a few quick guidelines. You want your files to be named with meaningful names. It can be a short name, but it needs to be a short name, but not so short that you can't figure out what it, Sam doesn't mean anything. So be sure that it's meaningful. Should be unique. One thing is to try and avoid personalized names, things like initials, because the truth is that, again, if you are transferring files after you leave the group, then it's not helpful to have to go back through and change all the old file names over to your naming protocol. If there are existing protocols, either in a, if it's a big research project, there may be some. If there's some in your labs, that's what you want to use. But again, if there isn't, create one. And pay special attention to dates. Dates can cause all kinds of problems. There are actually standards for using, for standard dates, an ISO standard. And the basic strategy is that you start with the largest unit, which is year, go to month, go to day, and then even include hours, time after that. And part of the reason why this is really important is because different countries designate dates differently. And you don't want to be confused about whether 0904 is September 4th or whether it's April 9th. All right. Again, unfortunately, I seem to have gotten a bit long-winded here, so I'm just going to draw your attention to this. This was an exercise that we have done in past workshops, where it's taken from the reference down there at the bottom, and they just taught their students about strategies for file naming using these experimental files. And it's NMR proton and carbon-13 NMR data and FTIR data. And they had first this is how the instructors organized it, but look how students did it, okay? Now, there is nothing wrong with the way the students did it, but by breaking it out into all these separate files and folders, if you are talking about a very large project and a lot of data, this is going to make it harder to find things. By using a good file naming strategy, as they did in the figure 1, this is going to make it much, much simpler to search for things. All right, better practice 5, apply appropriate metadata as you create as your data is created. Again, do it as you go, and that way you don't have to backtrack. This little diagram here just talks about, at the time a project is started, you know exactly what those files are and what those acronyms mean, but the longer you go, the less meaningful it gets, until by the time that the person who created it is gone, the information is completely lost. And this is how it is that that good data is completely lost. All right, so let's talk about metadata. Again, this is the documentation that helps you understand what your data is. And there are several levels of metadata. So you're going to describe your data. You can talk about everything from what's in it. You may include additional information about, this is analyzed data, this is raw data, this is, we have missing records here, et cetera, all of those things. And there's both the project level metadata, there is the file level metadata, and you can even have, metadata that's created at the data point level, okay? So it is critical for data discovery and reuse. You have to have that level of description, or no one else is going to be able to figure out what your data is. Okay, I introduced the term FAIR principles. We will not talk about that today, but if you are working with open data, you undoubtedly will come across it. And it basically just means that data should be findable, in other words, a Google search, accessible. Once they find it, can they get to it? Interoperable. Is there enough metadata provided that I can figure out which field in that data set lines up with my data? and reusable. All of those things combined to make it so that I can use that data. All right, best way, again, create a README file. It's very simple, use a text editor. Create a README file for a project and drop that into the to the drive where your files are kept. If you are, very likely you're going to need to have README files for different folders depending on, again, how your data is organized. Remember to include such things as software versions. If you haven't, if you're using, say, an instrument, an analytical instrument, what was the operating system? What was the software version? That kind of thing. And save it with your data files. Plan for data protection. Okay, this is one that I suspect many people overlook. And when we are creating our data, the last thing we want is for something like this, okay? It can be a disaster where you just lose your records through a fire or a flood. It can be something like, some new green bee, behind the ears person comes into the lab and deletes accidentally some things that they shouldn't have. And it can also be such things as hard drive crashes or even viruses in your software, that kind of thing. All of those things, you need to have a plan for what you're going to do if one of those things happens. And it's not just for disasters. Again, if you have good backups and have thought through ways to keep a copy in the cloud, then if somebody wants access to that data, wants a copy, it's much easier for you to get to it. The final thing to think about as far as a reason for good backups and good data management is lawsuits. Sadly, it does happen. This one is an extreme case. Probably many of you have heard about Duke University's research misconduct lawsuit, but I guarantee there were lots of researchers that had to go trying to locate records that were not easy to find. So plan for when things go wrong. So in terms of security, the best thing you can do is limit access to your data. So if that means locking your lab doors, locking your office door, locking things in your desk drawer, be sure to password protect. Again, if you have your the spreadsheet that you've just spent 6 weeks getting perfect, password protected, and that way nobody else can accidentally go in and, or heaven forbid, on purpose, go in and make changes that you don't want them to make. Data encryption. OSU has an encrypted server, and that is probably the best and most secure way. Think through what data preservation options you have. Hopefully you don't ever get to this point, but file recovery options, data rescue, ways to recover it when it looks like it's lost. One thing I encourage people to think about is that when you are planning a backup strategy, and you should be, think about it in terms of how much work can you afford to recreate, okay? So if you have it varies. If your data, it requires a week's worth of prep work to run one experiment, and the experiment takes 48 hours, and that's in essence one data point, then you're talking about 10 days to create that data set. You probably cannot afford to lose very many of your data sets if it takes you 10 days to create it. So set a reminder, or if you can find a way to do it, an appropriate automated backup is another way to do it. The simplest and lowest tech way to do it is just put a reminder on your calendar every Friday, or 8 o'clock in the morning every day. Go in and back your data up. So to finish here, basically, good data management is a lot like good dental hygiene. If you have good habits, it's going to prevent a lot of expensive and painful reconstruction. And with that, this is some of the resources. There's other links in the slides. And so feel free to go back in and look at those. And if you have any questions, please feel free to, you're welcome to ask them now, or you can contact me at any time. I'm happy to work with you with your particular data management needs.